All right, today we're going to talk about differential equations. This is another area where antiderivatives matter. So far we've been talking about antiderivatives with a constant added. And when you're doing definite integrals, the constant that you choose doesn't matter because it gets canceled out by the fundamental theorem of calculus. But there are situations where the constant does matter. And one particular situation where the constant does matter is these things called differential equations. Let's say what a differential equation is, or at least in this course. In Calc 1, a differential equation is a problem of the form dy over dx is equal to f of x, and y at 0 is equal to a constant that's given. So what the differential equation is asking for, it wants a function y whose derivative is f of x, but has a specific value at x equals 0. An example or two will suffice. Let's solve dy over dx is equal to x, where y of 4 is equal to 10. So dy over dx equals x means y must be 1/2 x squared plus a constant due to taking the antiderivative. But which constant is now specifically mandated by this situation here? We need to have 10 equal 1/2 4 squared plus the constant. So this is 16 over 2 plus the constant must be 10. So that means the constant must be 2. So the solution to this differential equation is y is equal to 1/2 x squared plus 2. And that is in fact a unique solution to this differential equation. Let's do another one. Okay, we're going to solve dy over dx is equal to x. Nope, that was the one we just did. Is equal to cosine x, where y at 0 is 7. Okay, so y is a function whose derivative is sine, or is cosine, so y must be sine of x, plus some sort of constant. Now, since y at 0 is equal to 7, 7 must be sine of 0 plus that constant. Since sine of 0 is 0, 7 is equal to the constant. So the solution is y is equal to sine x plus 7. Okay. Why are differential equations important? They occur quite often in science. Anytime something depends on time, a differential equation is often important. And one particular version, which we'll spend a little bit of time with today, is equations describing gravitational motion. Okay, it is known through experimentation that the acceleration due to gravity is almost constant on Earth. There are some slight differences for elevation, but they end up not mattering usually for doing these calculations. It is known that gravity accelerates matter at 9.8 meters per second, and it accelerates at 32 feet per second. Those are the metric and the imperial units. Now, just this fact of gravity accelerating in this manner allows us to solve some very specific problems. So let's take a look at this problem here. If a penny is dropped from the Empire State Building observation deck, which is in actuality 381 meters high. At what speed will the penny hit the ground? All right, so let's take a look at this here. Now, the fact that the penny is dropped from the Empire State Building at 381 meters high and is dropping due to gravity means we get the following differential equation. Let's just x of t is going to be the position of the penny. Then x prime of t we know is the velocity of the penny, and x double prime of t will be the acceleration of the penny. We know one of these things. We know the acceleration of the penny is equal to negative 9.8 meters per second per second. That is known. Right? We also know that at time 0, the penny is 381 meters high. So we're going to use this information to work backwards. Okay. X second derivative, the second derivative position is acceleration. So x double prime is negative 9.8. So that means that the velocity, x prime, is negative 9.8 times t, that's the antiderivative of 9.8, plus a constant. This constant is the initial velocity in problems like this. But we're just dropping the penny, so the initial velocity is 0. So the velocity function is negative 9.8 t. Now we can take another antiderivative to get the position. So we get negative 4.9 t squared, because we have to divide 9.8 by 2 for the antiderivative, plus some constant. Let's call this constant d. This is the initial height, or position. This we know is 381 meters. So this is our equation which determines the height of the penny at a specific time. What do we do with this equation? Well, we want to find out when does the penny hit the ground. Why do we want to find when it hits the ground? Because we can then use that to find out how fast it was going when it hit the ground. Okay, it's going to hit the ground when 0 is equal to negative 4.9 t squared plus 381. So we take 381, divide by negative 4.9. That's t squared. So t, using a calculator, is about 8.81 seconds. So it's going to take almost 9 seconds for the penny to drop. So the velocity at 8.81 seconds is going to be the derivative at of the position at 8.81 seconds. So this is negative 9.8 times 8.81. I'm using this equation up here. And this is about negative 86.4 meters per second. It's negative because the penny is falling. Okay, so it's moving at negative 86.4 meters per second when it hits the ground. The question is, would that hurt somebody? Well, I looked up for a bullet to break skin, it needs to go around 61 meters per second. So this is moving faster than what a bullet would need to move to break skin. However, a bullet is a good deal heavier than a penny, and so the penny has a lot less momentum. So I'm guessing this penny might not even break skin. The other sad thing is, looking this up, because of wind resistance, the terminal velocity of a penny is about 29 meters per second. So that's kind of sad. The terminal velocity means that the air resistance pushing up at a certain point because of the friction made by the falling penny, so much air is pushing up on the fallen penny as it's falling that it equals out the force of gravity, and then the penny doesn't accelerate anymore. This happens fairly early in the fall, so you wouldn't even need to drop it from the Empire State Building to get maximum, or to reach this terminal velocity. So the penny, unfortunately, is not going to hit at negative 86.4 meters per second. It's going to hit at about 29 meters per second, which is probably not going to break anyone's skin. Might give you a bad bruise. I don't know if it hit your noggin, it might give you a slight concussion. I'm not sure. But I don't think anyone's going to die from a penny falling from the Empire State Building. This is not legal advice. Okay, let's do another one of these motion problems. These are kind of ubiquitous in physics. All right. An object is tossed upwards at 10 meters per second, 2 meters from the ground. Find its highest point. All right. So we are told some things, okay? X double prime is always the same for these problems. It's negative 9.8. But we're told some other pieces of information. Tossed upwards at 10 meters per second. That means that the velocity, or x prime at time 0, is 10. And the 2 meters from the ground means that x at time 0 is 2. So we'll start with this second derivative and work backwards. If x double prime is negative 9.8, then x prime is negative 9.8t plus a constant. Here we know exactly what that constant is, because when we plug in 0, we have to get 10. So x prime is negative 9.8t plus 10. All right, that's x prime. Now we want to find x itself, the position function. That is going to be negative 4.9t squared plus 10t plus a constant. This constant tells where the position is at time 0, which is 2. So this is the function, negative 4.9t squared plus 10t plus 2. This is the position function. All right, now we want to find the highest point. That means finding the maximum of the position. Well, finding the maximum of the position is the same as finding a critical point, which means solving this function equal to 0. So the time of the highest point is when 0 is equal to negative 9.8 t plus 10. So that's 10 divided by 9.8 is t, which is 1.02 seconds. And then when we plug that back in to the position function, that's going to tell us how high we are. And that's what we're supposed to find. We're supposed to find the highest point. So we plug that in. That's negative 4.9 times 1.02 squared plus 10 times 1.02 plus 2. What do we get for that? Okay, 1.02 squared is 1.04 about. This is 10.2. This is 2. So 1.04 times 4.9 is, this is negative 5.096. We're going to add 10.2 and add 2. we get 7.1. So about 7 meters is the highest point that this object will achieve. All right, so that's the very basics of differential equations. You'll have some problems on the worksheet, and then you can take some time with the web work.